Good afternoon, everyone. I'm Afon, and today I'm going to talk about my dissertation project, which is machine teaching for efficient capability identification in multi-agent orchestration. My supervisors are Uma and also Francesco Conson. And so the core question of this dissertation is simple. So how do you learn who is good at what in a team of diverse agents when you have a limited evaluation budget? So imagine yourself deploying a system where you have multiple agents, human experts, AI models, and each with their unknown capabilities. Now, to understand who is good at what, you need to do tests. But however, if you do exhaustive evaluation of their capabilities, you need so many tests, maybe 200 plus task agent pairs needed. But you also have constraints, time, human effort, computational resources. And so you may only be able to do some evaluations, 50 to 150. So can you be strategic about this? Instead of testing everyone on literally every single data pairs, can you ask the most informative questions first? And this is the question that we are trying to solve. So this work builds on Uma's paper about online orchestration. So in this framework, a concept called onwards correctness is introduced, which is defined for an agent K. Its component is its current correctness in its current region. So a region is a category of tasks multiplied by its future expected correctness across future regions. Now, the gap in this work is that there is a key assumption that the current agent capability correctness is known. So our key question here is, how do you efficiently learn these capabilities with a limited budget? So we solved this prerequisite problem that the previous work is assuming. So we're trying to solve this by using machine teaching. So what is machine teaching? It is when you strategically select which tasks or data points to test on, rather than testing all of them uniformly. Think of it like when you have a student who's learning. So if it's just random training, you gobble that student with a lot of textbooks and data. But then the idea of machine teaching is that you have a teacher who guides the students in selecting which textbook or which information to consume first. So there's three key principles in this. First is strategic selection, in that you don't spread the evaluations evenly. You focus on high information tests first, where your answers, and the best tests are where success probability is around 50%, or where you have maximum uncertainty. So if you already know an agent is great at something, then you don't want to waste a test there. And the next is expected information gain, where you want to see how much will this test actually reduce the uncertainty about capability. And so like what I said, the best tests are where you have maximum uncertainty. So we apply this to the orchestration framework, where there's the teaching phase, where you kind of pre-train offline first with limited budget T, and you learn which the agent capabilities via strategic tests, machine teaching tests. And then you apply this to the orchestration phase, where you deploy these estimates and continue the learning. So why is this working? So it identifies the most informative agent task pairs first, and it converges faster than if you had random sampling orchestration. And this enables small pre-production evaluation budgets to achieve near Oracle performance, which is where you assume you have perfect knowledge of the agent capabilities. And so we tried several teaching approaches, and varying in what information they require. So the first is the omniscience strategy, which knows the true agent capabilities. And so you design tests using that knowledge. It's a theoretical upper bound, which is unrealistic. You don't have this agent capability yet. But this is what we're kind of seeing what the theoretical upper bound is. The next is a surrogate, where you don't know the agent capabilities, so you observe binary outcomes of the agent on certain data. whether it's a success or a fail, and you learn estimates from those observations, and then you use information gain to decide what to test next. So there's no privileged information about the agent capabilities, just what you naturally get from the tests. And next is round robin, which is there's really no strategy. So you test each agent or task pairs equally. And then there's imitation, where you use the task similarity metadata to inform the selection. And then there's the random, which is baseline. So you just randomly select tests. Now, in this, the key, the practical approach would be surrogate, where you use information gain, and then it requires those binary outcomes, no special agent capability knowledge yet. And yeah. And so in this work, we aim to have several core contributions. First is we try to decouple the identification from the orchestration. So in a traditional method, you would learn slowly during production. So you have agents and tasks, and then trying to see, okay, given this this data, okay, we slowly trying to understand the agent capabilities. But in this, in our approach, we're trying to separate into these two phases. So first, we teach machine teaching, which is offline and using those strategic optimizations, and then we deploy those warm start estimates online. And so we're trying to introduce in this work, we're trying to introduce several machine teaching strategies and show how we choose between them, and also trying to apply information theoretic criteria by using expected information gains, and then we try to validate these results across various scenarios, and also using three models: beta, binomial conjugate, truncated normal, and logistic normal, among a few. And also we want to see pretty much a systematic study of these machine teaching components and orchestration together. Okay, so the setup for this is that we have four agent scenarios. One is approximately invariant, where you have all agents being equally capable for every kind of tasks, regions. And then you have the dominant, where you have one star plane excelling in all regions. And then you have a dominant plus misaligned costs, where the best agent requires the most amount of cost. And then lastly, we're trying variant, where each agent excels in a specific kind of tasks or regions. And yeah, we're trying to measure mean squared error, convergence speed, so the time it takes to reach optimal agent capabilities, and also orchestration accuracy and the reliability, which is the variance of these performances across many runs. And so we already have some results. And so in terms of accuracy, we tried some orchestration algorithms without the machine teaching, and also using machine teaching. And we can see that without machine teaching, there's many variants across these algorithms. It's quite unreliable. There's a lot of failures that can happen. Whereas with machine teaching, the standard deviation is lower, and you have higher accuracy as well. It's more predictable. So yeah, we can see from here that machine teaching actually closes the gap that if you were to compare it to Oracle, where you have perfect knowledge of the agent capabilities, and also the accuracy closes, and even from Umang's orchestration framework, having 69.2% accuracy, there's also an increase. And yeah, just overall across the board, if you have machine teaching, you have increasing accuracy. So the insight from this is that machine teaching eliminates the cost of not knowing capabilities upfront. So you get a 10% accuracy increase overall. And in terms of efficiency, so we tried several. There's machine teaching strategies I mentioned earlier, and we tried if we have only 0 runs, 25 runs, 50 runs, all the way up until 300 runs evaluations. What are the effects? How quickly do they converge? You can see that there's a lot of gains to be had from 0 evaluations to 50 evaluations. The accuracy kind of it steeply increases, whereas after 50 to 100, the curve flattens, gains are smaller, and then after 100 plus evaluations, you start to get diminishing returns. So yeah, from this we can see that if you have 50 to 75 evaluations, you capture 95% of the total teaching benefit. It's practical, and you also get pretty good orchestration accuracy as well, and only 0.57% below the Oracle ceiling, which is the the dotted green lines. But then after 100 plus evaluations, it's starting to be not worth it because you start to not have any additional gains, minimal gains, and it's not justified by the returns. So yeah, the key insight from this is that you don't need to do machine teaching to perfection. There's a certain kind of optimal place where you get to do it, and we found that 50 to 75 evaluations is the cost benefit sweet spot. And next is results as well from the teaching efficiency across the different scenarios. So it'll be approximately invariant, dominant, then misaligned cost, and also varying. And it shows the mean squared error from this. So here we can see first analyzing the omniscient, which is where you the machine teaching knows the agent capabilities. For approximately invariant, actually the mean squared error kind of drops really quickly compared to the other ones, really requiring 20 steps. But then it also kind of overall for all of the other machine teaching strategies, it starts to it doesn't converge as fast as the other ones. But overall, like all scenarios converge quickly. Yeah, and and like in the surrogate one, which is the practical alternative, you have moderate convergence speed across the scenarios. So that's the green one. I think, yeah. It's like compared to the omniscient, it's quite heavy. And in the imitation, the orange one, it has imitation. It has the slowest convergence with the highest mean squared error plateau. So what does this tell us? It tells us that teaching is scenario dependent. So simpler scenarios converge fastest, complex scenarios take longer. Now, why is this the case? So that goes back to the way the agents are set up. So if some agents are equally capable in all kind of tasks, it begs the question of whether orchestration is really necessary, because you can just choose everything. But if you have some agents, each that is specialized in a specific kind of task, then you want machine teaching and orchestration to really choose. Okay, I want to choose that the best agent for that specific task. But yeah, also again, what this tells us is that omniscient dominates. That's true because you have all of the information there. Yeah, and also that surrogate is quite practical. It's only 1.3% below the omniscient while being realistic. So the key insight is that when agents are roughly equal in capabilities, teaching is very fast. When agents have specialized roles, it's harder to learn, and that teaching takes more evaluations, but still much faster than passive without machine teaching methods. There are several limitations to this work. First is that we worked with synthetic data, so the way the agents are set up and also the tasks capabilities that is on synthetic data of binary success failure. And so the impact is that the Bernoulli assumption may not hold for real human AI behavior, and in reality, validation on actual human AI teams can be messy. You need continuous performance data, and also you also have fixed regions in that the category of tasks are predefined, whereas in real life sometimes you would have additional tasks as well. So you would need to address how to handle those new category of tasks. And also you have stationary agents, assuming that the agent capabilities stay constant, whereas in real life agents can improve. Humans, we acquire new knowledge, or sometimes we also forget. And also we're using sequential teaching, and that you test one agent task pair at a time, whereas in real systems you might evaluate these in parallel. And so the summary of this dissertation work is that for orchestrating multi-agent systems, you require known capabilities of the agents, but then exhaustive evaluations is pretty expensive. So the solution is we try to use machine teaching to strategically identify agent capabilities in a pre-production phase using information theoretic task selection. And the results are you have faster convergence, and the gap between the oracle, where you have perfect knowledge, is closing, and also you have accuracy improvements as well. And in terms of impact, this can be applied to a lot of scenarios for human AI teaming, diagnostics, multimodal ML systems, and also in resource allocation programs. Thank you.
One of the benefits of the original machine teaching work was this now very famous diagram that shows that if you use SGD, convergence rate is something, and if you use machine teaching, you're able to converge much faster. Which of your plots helps show that convergence benefit?
So using
The original, the iterative machine teaching paper from way over through. It basically says that I can do some sort of batch variant of this problem, applying the samples that reduce my gradient the most, take a step, sample again, take another step. And that's better than randomly allocating examples. And so I'm curious, the benefit there is actually one that's a little bit more similar to regret, because you're actually saying, I know what my optimal, I won't say I want to converge to is, but my optimal capability matrix that I want to be able to learn is. So it'd be good to understand that. You had a couple that were candidates, but I wanted to know your thoughts on this. This is very good. You did a good job, but so get more precise on that.
Okay, so also try to hold on.
Yeah, something like this, right? Where you have this convergence plot of how quickly you're converging.
Yeah.
Now, the other thing that's silly, right, is that approximately invariant is very meaningless, right? Like it's actually quite meaningless. So I want to make sure that in the future we downplay that. That makes basically I can converge to the uniform distribution is not a sexy finding. Like anybody can. The thing that's interesting is that the strength of the varying profile. I'd like to characterize that. I was going to tell you and Francesca that. So like if I am like 80% better than you at a task versus being 5% better than you at a task, the ability for me to converge efficiently is not at all clear. And so if we make it some function of magnitude, and then the function of the set size, so the number of random variables I'm estimating at once, which you could do it over regions, but even if you didn't say the regions were granular, they were just skills that you were acquiring, that would be another thing to also throw out there. But I think this one in the bottom right
Yeah.
zoom in.
So you can see that.
Because that's the only interesting one.
But yeah, you can see that with the shading.
Yeah, exactly. And then some of it's like somewhat not as meaningful. But let's discuss that. So magnitude of varying profiles. Because if it's I'm very good, 100% accurate, you're 0% accurate, converging to that shouldn't take long, maybe, in principle. And then as a function of the number of those, you should be able to get another upper bound. And we could probably rederive an upper bound as well, which is assuming everything's stationary and all the fun things on the side.
Yeah.
We've been thinking about this in other contexts too. So
Yeah.
this is very good.